Okay, we are now moving to our third presentation, which is a research paper. And unfortunately, none of the authors could be here, so we're going to have another presenter who kindly accepted to present this work, but she's kindly asking that the questions can come to Slido since the authors are online and can answer your questions, so you can hear directly from them. So if you are also here in live, but you can ask your questions on Slido. So the third paper is entitled Incentivizing Exploration in Linear Bandits Under Information Gap, and the presenter is Yi Su. Yi, please come to the stage.
Hi everyone, I'm Yi from Google, and unfortunately all of the authors of this paper, they cannot be here due to visa issues. So I'm going to present on their behalf. And the author of this paper are Huazheng, Haifeng, Chuanhao, Zhiyuan, and Hongning. And so although they cannot be here, they will try to be in virtually at this time now. So if you have any questions regarding to the paper, you can just post your questions on Slido and they can try to help to answer them. Yep, so basically this paper is about incentivizing exploration in linear contextual bandits under the information gap. And you understand what information gap means in the later slides. So we consider the problem of interactive recommendation, which is basically like happens in every recommendation platforms. And we can think it as a kind of a two-party game between the system and the user. So basically, in each round, the user would take a recommended item, and both the system and the user will receive the reward of the item. So if you can think about, say, the reward could be like the revenue of or the profit in the like e-commerce recommendation. It can be like clicks in an advertisement or like news recommendations, or even like watch time or listen time in music and video recommendations. So basically, when anytime when a suboptimal item is taken by the user, both parties will suffer regret from it. And the goal of the system is trying to maximize the long-term gain or total utility like over a certain time period. However, it typically faces two challenges. First is that the user's preference is typically unknown to the system. And secondly is that the reward feedback is acquired on the fly, so it is online feedback. And it is not free, so it definitely, like if you recommend some like suboptimal item, you will suffer some regret from it. So that's to maximize this long-term gain. The system needs to be very smart in how to balancing exploration, like exploring new data to reduce uncertainty of the system and predict like more precisely about the user's preference, and also like exploiting its current own knowledge. So we know that this kind of problem have been formulated as multi-armed bandits. So in bandit formulation, basically for each item is kind of an action, and it's have like unknown reward distribution as shown here. So in each round, basically the bandit policy recommended an action to the user and then like collect its reward. So the goal basically for the system is trying to maximize the cumulative reward over like T round, or equivalently like minimize like a regret over a certain time of period. And we know that this is a very common traditional problem setting with many popularly employed solutions, such as like upper confidence bound, Thompson sampling, or like phase elimination. So in this two-party game, if you think about the user typically have a very different objective. So the user is kind of like mostly like we're myopic instead of being like we want to explorations. Specifically, we consider myopic user as the user who estimates the action's reward and always take the best action in hindsight. So basically, the users are greedy in some sense. However, in the long term, the myopic behavior might lead to like linear cumulative regret. This is because of insufficient exploration and also inaccurate reward prediction. So as a result, the best action in hindsight is not actually the best arm that we should play. So we can consider the example showing in this plot, where each arm is associated with its predicted reward and uncertainty, or like the confidence bound showing here. So what the myopic user will do is that it will follow the greedy choice and choose the pink jar with like 0.5 estimated reward. However, the red jar with 0.4 reward should be explored, since its uncertainty is large and has high potential of being the best action. Specifically, we consider the problem when we assume like linear reward assumption. So basically, each arm or each item is associated with a feature X, and the reward is a linear product of the feature and an unknown parameter theta. And specifically, we assume that the user predict its own reward with the classical linear regression with auto-regularization. That is also like ridge regression here. So recall in this two-party game, the system wants to minimize long-term cumulative reward, where the users there are myopic, they're only looking at immediate reward. So basically, to incentivize the user to explore, one mechanism that typically like the company will do is that trying to offer compensation, for example, like coupons or discounts in e-commerce. So previous works on incentive exploration show that the compensation should be large enough to bridge the reward difference between the exploratory action and the greedy action. So basically, like you need to put some compensation between the two items so that users can pick in their greedy like hindsight. So in incentivized exploration, the system goal is to offer sublinear like total compensation, like to achieve sublinear regret in the long term. Well, the system will want to follow a certain exploration strategy such as UCB. So we can again consider the example here. According to the upper confidence bound, the system actually wants the user to take the red jar with highest UCB, but suboptimal estimated reward. In order to do that, the system should offer sufficient compensation to the user to let them pick this instead. So in this case, we can calculate that the system needs to offer at least 0.1 compensation so that the user can pick this red jar. And this is exactly the difference of estimated reward between the greedy action, the pink jar, and also the exploratory action. And also this is the minimum required compensation that the system needs to offer. And when the users and system, they observe same contextual features and same rewards, basically the system knows users' reward estimation and can always offer this minimum required compensation to incentivize the user to explore. So in our paper, the first contribution is that we try to show that the total compensation to follow UCB strategy in this setting is in the order of dimension x times square root of t, which is sublinear to the time horizon t. And also dimension x is the dimension of the features that sharing by both the recommendation side and also the user side. So however, in practice, the users and the system, they may actually observe very different features, even though for the same arm. And that is what we call information gap between the two parties. So we denote like XA as the user side features and correspondingly VA as the system side features. So under linear reward assumption, there are two parameters like theta X and theta V that describes the item's reward RA. And also like I think both of them are trying to estimate the same reward. So both XA and VA, they are ground truth features, but we assume that they have different dimensions. So the user side feature is lower dimension, or we can think it is mapping in a low rank setting. And this basically means that features on the system side kind of are less informative or kind of redundant in some sense. So you can think an extreme example in this case is that you can consider that the least informative features of the system side is kind of one-hot vectors, where like the system only knows the index of the action, like without any action features. So basically on the system side, this is equivalent as a multi-arm bandit problem, but on the user side, they are kind of using their features to predict the item reward. So basically in this paper, we try to answer the key question is that how can the system compensate without knowing features on the user side? In this case, system does not know user's reward estimation and cannot just offer the previous showing the 0.1 compensation as in the previous slides. So in this paper, our solution is based on the idea that the system should infer how much compensation would be sufficient under this information gap setting. Specifically, we construct uphill confidence bound of the minimum required compensation, that is the R hat G minus R hat A, using the feature structure. So the compensation, which we denote as comp T here, only relies on system-side feature VA and the covariance matrix A constructed by the VA. And alpha TV basically is the size of the confidence ellipsoid, and it is a function of T. So the compensation here is the intuitive way to understand is that the compensation here is more than necessary because with high probability it is larger than RG hat minus RA hat, that is the minimum required compensation. So as a result, at each round, the system should offer compensation comp T to target item that is also following UCB strategy to explore. And the myopic user with high probability will take the recommendation considering this compensation. So in our paper, our second theorem showed that this total compensation under information gap is in the order of dimension V times square of T. So recall that in our first theorem, that is without information gap, we know that the compensation is linear to dimension T. So actually the difference between these two regrets, that is dimension V minus dimension T times square root of T, is exactly the price or the added cost that we need to pay because of missing information from user side features that they have on their hand. We also show that the first compensation lower bound for incentivized exploration in linear bandits. And actually this is also sublinear in T, showing that this amount of additional compensation is inevitable or necessary if the system wants to achieve sublinear regret. So we use this both synthetic and real-world experiments to show the effectiveness of compensation and also its impact on the information gap. So in synthetic data, what we did is that we randomly sampled features with user side feature like dx equals dimension of 5, and also the recommendation side with estimated contextual features like dimension 100. We simulated myopic user with ridge regression as we introduced before. And the green curve here actually shows that if the system do not provide any compensation, so basically the myopic user will suffer from linear regret, as you see here. And the blue curve represents that if there's no information gap, and both the system and the user, they observe the same user side features, so basically the system can estimate the user side preference very accurately as what the user estimated for itself, then the system can always offer minimum required compensation and achieve low regret. And the orange curve is where the system observed this high dimensional or a lot of unnecessary features in a less informative setup. Well, it can successfully incentivize exploration and achieve sublinear regret, as you see in the plot. So basically we can clearly observe that the cost of the information gap, basically that is the difference between the orange curve and the blue curve. So basically we can see that the compensation and regret are larger than the blue curves where there's no information gap. And we also try to test this in the real world data set that we have real item features, and we use PCA to get different dimension of the features. So the users are still simulated. Note that in the left figure is that the reward ratio against a random policy. So the larger the better. And we can see a similar impact of the information gap in real world data set compared to synthetic settings. So in this paper, basically, we explore the problem of incentivized exploration in the interactive recommendations. And we introduced there could be potential information gap between system and user side features. And we proposed a compensation design when under the myopic user settings, where the idea is trying to offer more than enough. So we show theoretically the compensation and regret upper bounds and also like matching lower bounds. And empirically, we both tried experiments results on synthetic and real-world experiments to show the impact of information gap. So there are some also interesting future work, such as like we can try to incentivize the users to follow other exploration strategies, such as Thompson sampling. And beyond the myopic user settings, actually some users may also explore, but following unknown exploration strategies. So this direction may also like interesting to explore. Yeah, with this, I will finish my presentation. If you have any questions, please ask your question on Slido, and the user is available there, or you can just email them for questions. Yeah, thank you all.
Thank you. Thank you, Yi. Yes, as Yi was saying, one of the authors, Chan Wao, is available on Slido, or they drop their email on Slido, so they are available to answer all your questions. So with this, we can move to the final talk of this session, which is another industry paper, which will have two presenters. One of them is Andrea Marchini, and the other is Valda Markeviciute. And they will be talking to us about AdaptText, a self-service contextual bandit platform. Thank you. The floor is yours.